Hey, 12th graders. So we are starting our first lesson of our last unit that we will ever learn, which is super exciting. We've been talking about it a lot about like what is happening, what's coming up, and we're now finishing what we know about in regards to calculus. So we've covered so far the one half of calculus where we've talked about derivatives and the idea of derivatives, what they are, how to calculate them to a certain extent. And now we're going to talk about the other branch of calculus, which is your antiderivatives, or in other words, integrals. So you'll see that we interchange antiderivatives and integrals quite a bit. They are the same thing. So just keep that in mind as we're going forward. That antiderivatives and integrals are the same thing. The use of antiderivatives is just to like further emphasize that it undoes your derivatives. So, to talk about exactly what it is and why they undo each other, I think it's best to think about it in our like tried and true speed versus distance versus time relationship, which we come back to a lot in calculus, to talk about like why the integral is undoing the derivative. So let's take a look for a second at what we know about derivatives. Well, with derivatives, we tend to have, in a lot of our real world situations, we tend to have this relationship of time versus distance. And with time versus distance, you can have all sorts of different relationships there. We tend to see it look something like this, where we start at 0, 0, and then we get closer and closer to the thing that we're trying to get to. If we're like driving in a car, right? We're like going further away from where we were before. Now, if we wanted to bring in the third element, right? We talk about distance, we talk about time. The third element that seems to be ever present, super crucial, is speed. If I were to ask you, what is speed? Well, you would tell me, well, Megan, that's distance over time. And I would say, you're so smart. You're right. It is distance over time. And it's this relationship right here, this relationship that speed is distance over time, where distance is your y value and time is your x value, that it harkens for us the idea of the slope, the change in your y over the change in your x. And it brings us to this idea of like, oh, our derivatives are just our slope. And that's where it kind of starts to come in as that. We've talked about this now for 2 units. So hopefully we're feeling pretty good. And so if we wanted to know what the speed was at this certain time, at this certain distance away, we would say, well, talking about that relationship at that instantaneous point, we would get that the slope at that point, or the speed at that point, is that. So if we were to kind of like come at it from the other side, right? So we've talked about like, okay, we're talking about time versus distance, speed, derivatives from this side. If I were to come at it from the other side, I would talk about it as an antiderivative, first of all, or as we like to call them, oh no, integrals. We would draw a graph as well. And we would have time on our x-axis, right? That x-axis tends to stay consistent. It does stay consistent when we're talking about this movement between derivative versus original. And now, if we're coming at it from the other side, now we want to put speed here on the y-axis. And you can see that like, okay, well, we're getting further away, but we're getting closer and closer. It's not necessarily a constant speed, right? If it was a constant speed, this would be a straight line. So we've got some sort of like change in speed as time goes on. Now, if I were to look at this and say, oh, speed, time, let's bring in that third element, the ever present distance. And I would say, hey, what's distance? And you would say, well, if I'm looking at this formula, if I'm trying to get distance by itself, I would multiply both sides by time. So distance really is just speed times time. And so it's coming back to that relationship from the other side and saying like, oh, Well, if I'm given speed and time instead, and I wanted to find distance, then it's a change in operation, no longer a division and now a multiplication. And what that means, if you're talking about like this dimension multiplied by this dimension, you're talking really about that area. Now, if it's a triangle, then it would be that time times speed divided by 2, right? It's that idea, though, of that multiplication in regards to this physical manifestation of that relationship. The graph is your physical manifestation of that relationship. If you're multiplying those two dimensions, you're really talking about the area within that spot. And so it's probably hard to think about the fact that area undoes slope and slope undoes area, but that is why, and this is the beauty of calculus and what's really cool about calculus is you're bringing in not just geometry, not just algebra, but this like beautiful marriage between the two. And so you're kind of stretching your intuition a little bit in regards to these relationships that you've already established to kind of encompass a little bit more. So if you're ever like, why are they undoing each other? This is kind of your very quick of like what that relationship is and why this is doing what it's doing. So let's move on from that. We've talked about, okay, derivatives. Now antiderivatives, we've got this idea of like, okay, it undoes a derivative. So if we ever wanted to move backwards, it undoes a derivative. It also tells us the area underneath a curve, which is kind of weird and crazy. But let's talk about real quick the monotony with finding derivatives, and probably not in the way that immediately came to mind for you, but in a different way. So if we were to find the derivative of a function, and I were to first tell you like, okay, y equals 8x, what is the derivative of that? Hopefully, you went ahead and wrote down that 8 was your derivative, right? It's the slope of this guy. You have 1 up here, so you multiply 1, and then that goes down to 0, it goes away. Hopefully, we're feeling pretty good about that guy. So the derivative here is 8. Cool. What if I said y equals 8x plus 5? What is the derivative? Also 8. What about y equals 8x minus 3? The derivative is also 8. This is true for no matter what variable I put here. No matter what, sorry, not variable, constant. No matter what constant I put here. No matter what number is here, as long as it doesn't have a variable attached to it, like x, right? I know c is also a variable, but c is a variable in regards to the fact that it's representing a constant. It's not representing a variable. So as long as I have some sort of number here, no matter what that number is, it could be 0, right? The derivative is still going to be 8. So there's this like monotony that goes on when we're finding derivatives. There's a lot of derivatives that come down to the same thing when your original function could look very, very different. And this c right here is your constant of integration, this plus c. So when we start to undo derivatives, when we start to bring it from this side of the table to the other side of the table, when we bring 8 to 8x, we need to always remember like, oh, there could be some other constant there that I don't know what that constant is. It just went away when I found the derivative. And you have to have a little bit more information in order to find that constant. That's going to be the second half of these notes. But for right now, all you need to know is when we're finding the antiderivative, when we're finding the integral, that there is some sort of constant here. There might be some sort of constant here that we just don't know what it is. And so we always have to put plus c when we're finding that derivative. It's just always. And hey, watch out. It's always forgotten. It is always something that you're like, oh, right, plus c. Oh, plus c. Oh, right, okay, right? So just watch out. It's always going to be forgotten. So something to write here when finding the antiderivative. make sure to always account for this by putting plus C at the end.